Hi, higher level. We're now going to look at calculating limits algebraically. Here are the properties of limits that the book talks about. This is true whether you're going towards any real number as x approaches any real number or as it approaches infinity. Here are examples just written with positive and negative infinity. You will probably just be assuming most of these implicitly anyway as you do your work and not necessarily writing them out through a proof. But basically what it's trying to say is you can break up these expressions and these limits into various different pieces, much like you would any other kind of function, and work on smaller pieces. So I'll give a few examples as we're going of where that might be able to be done more explicitly, but really you might see these come up and you just know that you can split things down and consider pieces slightly differently in general. What's really important in calculating limits is that there are some forms that are indeterminate, which means if you get them when you try to substitute a value, for example, you're actually not really done. You're going to need to manipulate your expression or use some analysis, use some identities, some other different strategies before you can say that you have found a limit or that the limit does not exist. So there are quite a few. You'll most commonly see like 0 over 0 or infinity over infinity. There are some that are actually okay that kind of look like this, like 1 plus infinity, for example, is fine. Those kinds of things are not an issue. So keep those in mind, especially 0 over 0 is going to be one you see a lot. And as we go through the course and later, we're going to have other strategies that we see again, but for now, we're just going to take a look at some of the algebraic strategies to calculate limits of expressions. Here are your basic strategies for calculating the limits. We saw some just in class today as we were talking about it. Evaluate the function at a given point. If there's no issue, if you just put in the value as x approaches into your expression and don't have a problem, then you found the limit. Sometimes you may need to factor it, cancel things out, and then try again, evaluating the function, and it's going to work fine because you've removed the issue. That might be that you put in x equals 4 or whatever, and you get 0 over 0, and then you factor out that particular factor of 0 and 0 at that value, and you get something that's no longer an indeterminate form. You can also try factoring out the largest power found typically in the denominator. Technically it does work. I'll talk in an example about why the denominator is the one often used. You can apply some of the properties of limits either explicitly or implicitly, depending on how the question is set up. And you can use other identities or conjugates, like with square roots, multiplying in order to just change the way the expression looks, even if you're not changing actually what the values kind of are. So we're going to work through quite a few different examples of how these could be presented now. Here's a basic one. What is the limit as x approaches 2 of x cubed minus 5? If you put in 2 for x, you don't have any issues. So that first thing of just evaluating works just fine. The limit as x approaches 2 on this function is 3. The curve is just going to pass through the point 2, 3 without any issues. Here's another example where you may see, however, that if you put in 3, you're going to get 0 over 0. But what we can do is try factoring, because that quadratic factors to x plus 4 times x minus 3, and you can cancel out the x minus 3's. While there is a hole in the original function at x equals 3, it is otherwise basically the same as the line x plus 4. And if you put x equals 3 into this expression, you don't have any issues there. So as you approach x equals 3 from both sides, you're approaching 7. Here are a few examples that are a bit more challenging that we can't just factor, or that we might need to use some of the other strategies for. If you put x equals 0 into sine of x over sine of 2x, you'll get sine of 0 over sine of 0. And sine of 0 is 0. So you're going to get 0 over 0, which is a problem. But you can use one of these identities for sine of 2x. There we have the 2 sine of x cosine of x and cancel. Okay, and you get that this is basically the same as 1 over 2 cosine of x. And if you put in x equals 0 into 2 cosine of x, you get 1 over 2, which is not an issue. So it's approaching the value of 1 over 2 at this point, even if it's not exactly equal to it. Here are two more that look very similar, but have some intricate little details that may make it a little bit interesting. Here is where x is approaching infinity, positive infinity in this particular case, but the same strategies can be used for negative infinity. Just keep in mind what the negative might do if you're multiplying or dividing by a negative. They're both rational expressions. We've talked about what the asymptotes could look like here, horizontal, vertical, oblique asymptotes are things we've seen at higher level. As x approaches infinity, this will be something either like a horizontal asymptote or an oblique asymptote, but going to the sides and not a vertical asymptote where you're approaching some real value and going up or down, so to say, forever. There's no way to just evaluate this. What's happening when you get infinity over infinity? If we were to put this in, 3 times infinity plus 4 is just a bigger infinity, and 2 times infinity plus 5 is just bigger infinity, and infinity divided by infinity is indeterminate. There's no factoring where both a factor in the numerator and denominator can come out. So the strategy we're going to use is to divide by the highest power of x in the denominator. In this case, it is the same as the numerator, so it doesn't really lead to any weird questions of why. What will be nice if you do that is you're going to be dividing by infinities. And what happens when you divide by infinities, you see in this first piece I've canceled out the x's because it's in the numerator and the denominator. But when you put in infinity for 4 divided by infinity or 5 divided by infinity, as you divide by bigger and bigger numbers, they get smaller and smaller. So you're actually saying, well, this is basically the same as 3 plus essentially 0 over 2 plus what's basically 0, and you get 3 halves. So you could actually look at this function, or you could see, based on what you know, as you approach positive infinity and move towards really high x values, you're going to approach 3 over 2, y equals 3 over 2. I didn't mean to go on to that right away. I was just going to highlight that. You can probably remember that this, if the degrees are the same, we're comparing, there is our horizontal asymptote. Okay. Here's the algebraic proof of this. If you're looking at something where the powers are not the same in the numerator and the denominator, like in the second example with x going to infinity, you're going to get something that's a little bit more interesting, I will say. You typically find that they recommend to say divide by the highest power you see in the denominator. You can actually do it in the numerator. It's just not going to be as elegant in the sense that you're going to get something that you may need to think about what it's approaching a bit more. Because dividing by 0 still presents problems. And while you can kind of think through what's happening in these, and non-indeterminate forms are not going to show up, it's just going to be a little bit easier to think of, we have a 0 in the numerator but not the denominator. So you can see here the highest power in the denominator is x cubed, and what we're going to do then is divide everything in the numerator and everything in the denominator by x cubed, factoring that out and canceling it. And this is what we'll get in both the numerator and denominator. And now with the same logic as what we saw before, all those things with an x in the denominator are going to go to 0. We do still have that this minus x, the minus infinity, is going to be minus infinity, which is fine. Minus infinity divided by 1 is not a problem. It's not an indeterminate form. It is going to negative infinity in this case. Just again, be careful with those negatives and positives. And this makes sense based on also what we've talked about with rational functions. As you were to divide using long division, you would see that you will get an oblique asymptote. But even oblique asymptotes are going towards infinity as you go towards infinity with your x values. Here are a few more examples. We have the same problem approaching two different particular values that are going to do two different things. In both cases, if I were to put x equals the square root of 5 or x equals 0 into this, I'm going to get an indeterminate form, 0 over 0 problem. In the first case, factoring out the numerator is the difference of squares, x squared minus 5, x squared plus 5, and pulling the x out of the denominator is going to get another x squared minus 5, and those can cancel. So we get an essentially equivalent expression that won't have the same problem. I can put in the square root of 5, no issues. We should avoid the idea of having a radical in the denominator, but you get a nice value, right? You can see the working right there. Whereas if I try the same strategy here, I've just taken the factoring that I did already up in the first problem, I still get this indeterminate form of dividing by 0, or it's not an indeterminate form, I should say it's 5 divided by 0. You could think through that. This is the same reason why you tend to divide by the highest power in the denominator. But if I were to divide by that, what you'll see more elegantly is that you are going to have a term with x in the denominator here that will go towards infinity. You could break it down and see the same thing you saw a little bit earlier as well. That first thing will go to 0 and the second thing will go to infinity, and you'll get that this goes to infinity. Here you could also see, well, we're getting 5 divided by things going towards 0, which is going to go to infinity as well, even if you didn't break that down quite as far. Here's one that looks quite a bit messier. It is. You can still think of breaking this up into different pieces. So here I could now say, well, this is the limit as x goes to infinity of negative square root of 4x plus 3 over x plus 1 plus the limit as x goes to infinity of 7 square root of 2 plus x over x plus 1. You could then say, well, pull out the coefficients and break that down more and more. But really we're just splitting it up in the same idea without rewriting the limits, okay? Just splitting it up. Those are still going to have the same properties that we see. And as you break this up into different pieces using some of the laws, like this right here is if I have a square root of something divided by a square root of something, I can put them both in the square root. That's not a problem. And then you can factor or pull out the highest power of x in the denominator, which I've done similar already to the past problems in both of the pieces. And if you then plug in infinity, in this case, that's 3 divided by infinity, and the 1 divided by infinity, and the 2 divided by infinity, 1 divided by infinity, those are all going to essentially 0. No longer with the limits, because we're saying, okay, let's put it in and say kind of what that is. And we're getting then that this equals, well, square root of 4 over 1 is square root of 4, which is 2, times the negative is negative 2. And that second piece is 7 times the square root of 1, so 7, and that would equal 5. Again, same ideas of splitting this up, the same laws we've seen before, just take it piece by piece and make those equivalent expressions. This is also applying to convergence when we talk about sequences. If we say that the limit exists and it's a real number, then we can say it converges, just like we saw when we had the sum to infinity in a geometric series. So imagine you have this sequence, just because they're calling it a sequence, or if they call it a series and you have to add things up, you can find an expression and say, well, what's happening as I approach infinity? Regardless of whether this is x or n, or whether they say this is a sequence or expression, they're going to work the same ways with the same properties. So I'm going to divide in this particular case by the highest power of n that I see in the denominator, the n cubed, factor that out, and I have this little bit simpler of an expression where if I put in infinity into a denominator, those pieces are going to 0, and you get 1 plus 0 over 2 minus 0, and that equals a half. So this is why we say it converges, the sequence converges, because the limit is a real number and not infinity.